Now we go to the heavy part of simple harmonic motion. You should be looking at page 7. Okay. All right, now, when you have something that moves with simple harmonic motion, because it involves motions, you need to be able to describe the motion of something that moves in simple harmonic motion. Normally, when you want to describe something that moves, you would try to describe it in terms of its displacement, in terms of its velocity, as well as its acceleration. Okay, this would be some of the common terms you use to describe the motion of something that undergoes SHM. If I tell you I have a circle, like the ones that is being shown on your screen right now, and then this one being the center of my circle, and I have some sort of reference line here. Let's just say that I have a reference line here. Let's just say, for example, I have a point over here. And then this point here is moving in circular motion at constant speed. Okay. This point here moves to this point, to this point, to this point, and then to this point. Let's call these points respectively as point A, point B, point C, point D, and then point E. Okay, so I have a point A here that moves from A to B to C to D to E at constant speed. Let's just say, for example, maybe it moves at 5 meters per second. All right. So as it moves counterclockwise from A, B, C, D to E, you are interested in finding out the displacement of that point from a particular point, which is your center of your circle. So in my case, I am interested in knowing displacement for A. My displacement for A now is actually just 0. Let's just call this XA. My displacement for point B, this one would be XB. Displacement for point C, this one will be XC. Displacement for point D, this one will be XD. And then for point E, this one will be XE. Okay, they're all measured with respect to my center position. Okay, I'm measuring the vertical displacement from the center point. Now, if I want to plot out a certain graph as the point moves in a circle, what we will say is that you tend to get something that is sinusoidal, a graph shape that is sinusoidal. If I try to plot for you a graph of displacement versus time, the graph shape that you will expect to see as the point moves about is a sinusoidal graph like this. Okay, so this part here would be where you have point A. This part here will be where you have point B. And then this part here will be where you have point C. And then this one is D. And then this one is E. Okay. So if you were to try to plot the displacement of your points with respect to your time, this is what you expect to see. Okay. So this one, I can say this one is XA, XB, XC, XD, and XE. So this graph shape that you have is what we call a sinusoidal curve. Okay. Now, sinusoidal doesn't mean it must be a sine graph. A sinusoidal curve just means that it follows a wavy pattern like this. I could give you a cosine graph. We will still call it to be sinusoidal also. If I have a graph that looks like this, if I tell you about a sinusoidal curve, it can be something that looks like this, a sine graph. It can also be something that looks like this, a cosine graph. Okay, both are still called sinusoidal curve. Okay, just because you see the word sine here doesn't mean it must be a sine graph. It can also be a cos graph. Sinusoidal is actually really referring to the curvy shape that you see here. Okay, so here the main point that I just want to illustrate to you is that for any point that moves in uniform circular motion, meaning to say it moves with constant speed, the variation of its displacement with respect to a reference line with time is going to be sinusoidal. Okay, so now what you want to do is that you want to compare the motion of a pendulum bob that undergoes simple harmonic motion to something that moves in circular motion. In your case, you're comparing it to a rod that is set up on a rotating turntable as shown. See, this little diagram that you see here is actually talking about a point that moves in a circle. Okay, so just now I already told you, if you have a point that moves in a circle at constant speed, the displacement with respect to time will be sinusoidal. Okay, so here, this point that moves in a circle, in this example, they use the example where you have a rod that's set up on a rotating table. Okay, it is actually this part here. You have a rod, you put it on a turntable, the turntable is moving in a circle. This diagram that you see on the right is kind of like the top view of the turntable, of the rod on the turntable. Okay, so the thing here that you should see is that this rod moves in a circle like this. Okay, it's moving in a circle like this. Okay, so from there, what you want to do is that you want to put another object that's undergoing simple harmonic motion, which in your case is a pendulum bob. Okay, so you make sure that as the turntable is rotating, causing the rod to move, you make sure that your swinging pendulum has an amplitude of oscillation equal to the radius of rotation of the rod. So what we mean by that is that if you see this rod here, as it moves in a circle, it would have a radius of rotation of r. So for your pendulum bob, when your pendulum bob oscillates back and forth about your equilibrium position, it will also have an amplitude position, right? So you make sure that your amplitude position matches your radius of rotation of your rod. And then also at the same time, you make sure that the rotation speed of your turntable is adjusted so that the time for one complete revolution, meaning to say the period for one complete revolution here, is exactly equal to the period of the pendulum. So the pendulum bob, when it oscillates, also has its own period, isn't it? So you make sure that the period of your pendulum bob is the same as the period of your rod rotating on the turntable. Okay, now what you want to do then is this. You try to shine light onto these two systems. You shine light onto these two systems, you put a screen behind them, and then you observe how the shadow moves. You see, when the rod is moving in a circle and you go and shine a light right at the front, you're going to get the shadow image like this. Okay, you're going to get the shadow image of your rod right over here. Now, because you're just looking at the front perpendicular to your screen, what you'll see is that your rod is actually just moving sideways, left and right. The shadow image of your rod is actually moving left and right. And then as for your pendulum bob, you will see that your pendulum bob, again, because you're seeing it perpendicular to the screen, your pendulum bob, the shadow image will again just move towards the left and then towards the right. Okay, so what they found out is that as your pendulum bob moves, the motion of your pendulum bob matches that of your rod oscillating left and right. Okay, here we mentioned that the whole apparatus is illuminated from the front so that a shadow image is formed on the screen. They saw that the shadow of the pendulum bob swinging is actually moving exactly the same as the shadow of the rod moving around its turntable. Okay, so it's from here that you can actually come to one conclusion saying that simple harmonic motion can be assumed to be a projection of uniform circular motion for which the displacement from equilibrium with time follows a sinusoidal curve. Just now earlier, I mentioned to you when something moves in a circle with constant speed, its displacement with time tends to follow a sinusoidal curve. Now, when you go and compare with the motion of a pendulum bob, the motion of the pendulum bob follows exactly the motion of your coin that's moving on a circle, which is your rod on a turntable right now. So because the motion in the circle is sinusoidal and pendulum bob moves exactly like something that moves in a circle, you can therefore say something that moves with simple harmonic motion, the displacement with time will also be sinusoidal. Okay, so it'll be easier to see an animation from here. Okay, now on your screen right now, you should be able to see some sort of video playing. Okay, so you'll be able to see two objects right now. Okay, let me just pause the screen for a while. Okay, let me just pause it here. You will see two different objects on the screen right now. The one on the right is something that is following circular motion. You can think of this as the rod on your turntable. And then the diagram on the left is showing a mass spring. This one, you can assume it to be following simple harmonic motion. Okay. So if I start to play the animation, you just look at how the pendulum bob moves up and down and how the green color ball moves in the circle. You will see that the motion is exactly the same. They match with each other. If this one reaches the top position, both will, if one of them reaches the top position, the other will also reach the top position. If one of them reaches the equilibrium position, the other will also reach the equilibrium position. And then likewise, if one of them reaches the bottom position, the other will also reach the bottom position. Okay, that's why we can say that something that undergoes SHM will also tend to follow circular motion because the motion matches exactly. Okay, and then from there we can say that your displacement with time is going to be sinusoidal. All right, so back to the notes. Okay, so from there, if say your question asks you to determine the displacement of an object that follows simple harmonic motion, there's a particular equation that you can use. All right, so let's just say, for example, if we consider a system that undergoes SHM, such as the mass spring system previously, I told you that the displacement time graph can be described as being sinusoidal. Now, your graph shape is sinusoidal. It can be a sine graph, it can be a cosine graph. The graph shape actually depends on the starting position and the initial direction of your motion. What do I mean by that is this. If say, for example, you had a mass spring system, it was going from the equilibrium position, it was starting from the equilibrium position going up, you will see that it's right over here, it went up, then it went down, and then it went back up again in this manner. So if you were to try and visualize its displacement with respect to time, it will be at the equilibrium position going up. So your graph shape will be something like this. Now, when you have a graph shape that is like this, the equation that represents this graph shape is generally x equals to x naught sine omega t. There will be a sine function here because it's a sine graph. Then after that, it's really a matter of just replacing your variables here. Because if I'm not mistaken, last time when you guys learned this in maths, this one is y, this one is say theta. If I tell you that this is a, this one is y equals to a sine theta, right? You learn that omega is theta over t. This one is in circular motion. So theta is omega t here. So you sub this one in, you're going to get a sine omega t. All right, that's how you get this graph shape. Okay, so the derivation of this, you don't need to know lah. You just need to remember that if you have this shape, then generally the equation is like this. Okay, so this one is for one case where your object is going the equilibrium position going up. There will be some other cases also, where we tell you that it could be that your mass was from the top position going down like this. So it started here, went down, went up, and then went back down again in this manner. Okay, so you started at the top position, you went down, you're going to get a cosine graph. So this one will be x equals to x naught cos omega t. Your x naught here is actually your amplitude, okay? Then if you have something where you started off from the bottom position, going up, you go up, you go down, you go back up again in this manner. So you start from the bottom position, you go up, you get a negative cos graph. So it's x equals to negative x naught cos omega t. Okay, so if you want to find the displacement of an object that moves with simple harmonic motion, generally this is the equation that we will use. Okay, but which equation specifically depends on how the object started off and what was the initial direction of motion. Okay, questions like this actually don't come out quite often. They actually came out only once or twice in the older past year. All right.